Okay, well, welcome back for our third time together. Is this on? Okay. Can you all hear me well? Good. Um, so, um, happy to be moving through the week, and that was a great poster session out there. A lot of good science happening here at Les Houches. So, what I'd like to do with our time together this afternoon is get to the point where we have a shared language for describing noise in an interferometer and comparing it with signal strengths. And so for a good portion of this lecture, I'm going to be talking about what one needs to know to interpret noise power spectra, because that's the language that we use. And I'm going to do something that's somewhat unusual for me, namely use a fair amount of mathematics. There will not be more than one equation per slide, so it won't be as mathematical as some of the other lectures you've been treated to. But for me, it's a lot. And then I'll apply that to the one very important noise source of shot noise in an interferometer. And along the way of explaining shot noise, I'll be describing some of the optical tricks that are used in interferometers to make the shot noise as small as possible. I'll say a bit about radiation pressure noise and the quantum limit, pick up a bit more on that when we get together again tomorrow. And just to look ahead to tomorrow's lecture, there I'll talk about several of the other important noise sources that govern the sensitivity of interferometric detectors. So here's a slide that I left you with last time. I was accused of being a master of suspense or something worse. But there was a moral point to all of that, namely for us not to take for granted how hard it has been, and to have patience for whatever pace comes our way for improvements. It is possible to make these things work, as we know. If you want to learn more of this kind of material at the kind of style that I've put it together in, you are welcome to purchase a copy of my book. This is what the cover looks like in the second edition. For anyone who has the first edition, you won't find much difference, so it would be immoral of me to say you must buy a copy of the second edition. Second edition has a chapter 17 epilogue, which is there to bring things up to date, but I did not have the patience to rewrite every part of the book. So if you have a first edition, first of all, thank you, and second of all, is probably pretty good for your purposes. Okay, this is the key diagram for today's discussion and also tomorrow's discussion. I'm sure everyone in this room has seen a graph like this, and I'm sure that some of you all are masters of understanding what it says. And for those of you who are, I will ask for your patience while I make sure that everyone else at this summer school will leave the summer school knowing how to read diagrams like this and what we can take from them. So this is the noise power spectrum. I picked, for illustrative purposes, the advanced LIGO spectrum that was appropriate to the time of the discovery of GW 1509-14. So let's look at what's on this graph, and then we'll build up more and more sophisticated understanding of it during this afternoon. So it's a log-log graph, logarithmic frequency scale on the x-axis, logarithmic scale of something to do with noise on the y-axis. Let's read what the legend says: displacement in units of meters per root hertz. So before we're done, we'll know what can possibly be meant by those strange things, meters per root hertz, what displacement it is that we're measuring, and we'll also understand why typically there are usually a bunch of different curves on this graph. The most important one is this red one labeled measured. That represents all of the noise in the interferometer expressed in these units at that time. Everything else is either a measurement or a calculation of a particular contribution to an expected contribution to that total measured noise. We'll be talking about this blue curve, the one that's labeled quantum, but that I will interpret as a combination of a shot noise curve and a radiation pressure curve. Tomorrow we'll be talking about, well, let's see. First we'll talk about this brown one, seismic. We'll talk about some more about the radiation pressure part of the quantum noise curve. The green one labeled thermal, and you can tell by its shape, it's got something of an interesting story to it. There's several different regimes for that. I won't have anything to say except over meals or over coffee about the Newtonian noise. And something you should make sure you spot here and every time you see a graph like this, the noise budget of an interferometer like LIGO consists of a list of every noise that we think we understand and know how to calculate, and then their sum, and the sum of the ones that we hoped would be involved is the blue, the green, the brown, and the orange, and they're far from summing up to the red. This gray one has the suspiciously obscure title of Other Degrees of Freedom. A lot of it, but not all of it, is understood. But of all of it that the people who compiled this noise budget graph could understand is there in gray. They a little overestimated it up here. But you'll notice there are several frequency regions where even adding in that other degrees of freedom noise, there's still a gap. So this is your indication that commissioning interferometers is a challenging business beyond even designing them and installing them, because when you put everything together, there are still mysteries. Fortunately, not too many, and fortunately, as we know with very happy hindsight, this overall noise was sufficient to get us into the business of detecting gravitational waves. So I want us to leave today understanding what this graph can mean and understanding in particular the shot noise part. And by the end of tomorrow's session, we should understand most of the curves on this graph. Okay, so the words that are written on this slide are my apology for switching into mathematical mode, which is not my favorite place to be. It's not very dignified mathematics. I'm calling it applied mathematics in quotes, and then we get applied physics. That I'm actually really proud of. One of the things I personally think is coolest about this business is that in order to make gravitational wave detectors work, you or one of your buddies working next to you has to be a master of lasers, optics, quantum optics, thermodynamics, mechanical engineering, vacuum engineering. The list of physics and engineering topics that goes into a successful gravitational wave detector is, to me, awe-inspiring. Okay? So maybe I'll leave you with a bit of appreciation of that as well. The first thing we need to do, and the thing that I'm going to use mathematics for, is understanding in particular the various ways one can describe a time series. And my goal is that we'll be building up intuition about what these various descriptions of a noisy time series might mean. So fundamentally, we start with something we can write as x of t. There's actually a whole bunch of different examples where something of the form x of t is what we are interested in. I've shown you as, well, has anyone else shown you strain curves h of t yet? I'm not sure. Okay, but I've surely shown you some. And they are a prime example of what I'll refer to as a deterministic function of time. And that may seem odd until I contrast it with a random function of time, such as the output of an interferometer that's sitting there waiting for a gravitational wave to come by. Now, you can draw them on the same kind of graph, and in fact, you know, when you plot them, their units are the same, and it may not be obvious at first which you're dealing with, especially because what we hope to be the case from time to time is that we're actually, when we're looking at the output of an interferometer, we're looking at a mixture of a deterministic time series from a signal superposed unavoidably, unfortunately, on the noise. And so we want mathematical tricks that let us know when we've got that signal in the presence of noise. And this is actually a part of a huge fraction of experimental physics, but we're kind of in an extreme limit where, you know, we're trying to do astronomy, and for a long time we were getting no signals for years and years and years. Now we get one signal of a few seconds duration maybe in a month. Most of the time we're still looking at noise. So knowing when a signal is going to be strong enough to be found, that's the point of all of this. So as a guide to what I'm about to show you in the next several slides, some of the operations we'll do on a time series are best thought of as a good way of characterizing a deterministic time series. Others make more sense when you're applying them to a random function of time, and then you have to know what will come out when you are looking at a mixture. Okay, so the foundation, if x of t itself is not the foundation, the foundational operation that we can perform on a time series, or one of them anyway, is the Fourier transform. And so there's probably no one in this room who has escaped encountering a Fourier transform before, but let's make sure, A, that you see my notation, so you won't get tripped up by notation, but also I want to take the opportunity to share with you my intuition about these kinds of objects. So we've got our time series there, and we multiply by this oscillatory function, an exponential of minus I 2 pi ft, and a lot of people would write omega. I chose to write 2 pi f because when an experimentalist draws a frequency scale, it's always f in hertz, so let's do it. So this is the integral that defines the function of time that I'm going to call capital X of f to go with lowercase x of t. And the intuition you should be carrying about the meaning of this operation is that it tells you how much of a sine and a cosine of each frequency you would need to sum up together to, after you've summed them all up, reproduce x of t. And because you're keeping separate track of the sines and cosines, I'll assert that this is most useful to stare at when x of t is a deterministic function. But it ends up being as part of the foundation of many other tools, so it's really used all over the time. So you will often hear people saying, all right, enough of this stuff in the time domain, let's look at the problem in the frequency domain. What someone means by that when they say it is, let's take a Fourier transform or something very much like it. I'll tell you a personal story. I started learning frequency domain methods when I started my first postdoc with Ray Weiss, and I was so charmed with everything you can learn, so I'm going to be an apostle for that. But at some point, I realized that we actually live in the time domain and just visit the frequency domain. So it's no matter how much insight you get out of frequency domain methods, you have to understand what it means back in the time domain where we live. And sometimes it's good to remind oneself of that. Okay, here is an operation that doesn't go into the frequency domain at all. This is an operation you can perform on two time series, x1 of t and x2 of t. And we call this operation the cross correlation. And what is it? Take the one time series, multiply it by the other time series, shifted by an offset, tau, and integrate over all time. And then what that gives you is this object x1 cross-correlated with x2, which is a function of the new time variable, the time shift. And so let's build up some intuition on what this is all about. This is a measure of the extent to which the one time series, x1 of t, looks like the other time series, x2 of t, yes, without requiring that they do the same thing at the same time. It hunts for similarities as a function of this time shift. Now, I'm going to assert that that seems like, geez, why would you ever do that? But it's unbelievably useful, and my favorite way of demonstrating to you that it's useful is that the case of searching for a signal of known shape in noise, which is a problem that we do all the time. So here is a graphical way of explaining how you can use the cross-correlation operation as a way of helping you to find signals in noise. So this might be the output of an interferometer, say, or of some other measuring apparatus where you suspect there might be a signal and you think you know what the temporal form is of the signal. And in the second graph, also a function of time, also a time series. First, let's look at the blue trace. So this shows a sawtooth shape that is an example of the model you have of the possible signal buried in this noise. Now, this one's not so buried. You can probably see why I was especially happy to line it up there, but I didn't have to line it up there, and in fact I wouldn't to start with. I would line up that interesting part of the signal there, and then there, and then there, and I've actually sketched in a few possible time shifts tau, including this magic one. And for each value of tau, the cross-correlation operation invites you to point-wise multiply those two time series and then integrate, and you get a number. Now, what we see in the bottom graph is the result of performing that operation as a function of the alignment of the signal model with the data. When there is no signal of that shape in the data for the particular place where the interesting part of the template's been aligned, you get some value of the operation, but you're basically just filtering that noise, okay, and nothing interesting happens. That operation is designed so that when you happen to align with a part of the time series where a signal of that shape has been added, then all parts of that section of the time series end up contributing in a positive way to the integral. The parts where the template is positive, on average, are going to give you multiply with this positive part, and the parts where the signal template is negative, well, you expect on average the output of the interferometer to be negative, and so they contribute also to a positive part of the output. So now if we look at this time series, which is the time series of the cross correlation, we see that we've built up a rather nice peak. There's still noise, but the noise is smaller because we've averaged all those noise points over a bunch of different times, the duration of the interesting part of the template. And so the signal to noise ratio of this output is larger by a visible fraction than it is at the beginning. And let's make sure that that your eye is telling you the same thing that my eye is telling me. So, how big is that sawtooth in the original output? Well, it's about this big or about that big. So in the units I drew here, it's about 5. Okay, but how big is the noise? Well, how do we characterize the noise? A typical value of the wiggles, maybe it's about 1-ish. Yeah. Okay. So the instantaneous signal to noise ratio there is about 5-to-1. But what this is telling us is that actually the achievable signal to noise ratio by this operation, which goes by the name, we've probably all heard it, matched filtering, is better, because now we've got an output here of 100. This is maybe 5 or something. So we started with a signal to noise ratio around 5. We end up with a signal to noise ratio around 20, just come from averaging a number of points where the signal adds coherently in that average, but the noise just adds up incoherently. So that's the basic idea of matched filtering. You'll hear a lot more about it from Alan Weinstein next week, but this is the basic idea. Of course, when you hear about it from Alan, you hear about it in a situation where it's technically more difficult to apply, but where the gain is potentially much higher, okay? Signals from binaries where you might do this over 100 cycles or maybe 1,000 cycles, something like that, where you can get really tremendous benefits. Here, for illustrative purposes, I just made it so that you could see what was going on all along. Okay, so the cross correlation is a fabulous operation. To go back to my comments about time domain and frequency domain, if you're actually going to compute this, you'll do it in the frequency domain. But if you can't draw it and see what's going on in the time domain, you won't understand what that much faster frequency domain code will do. So there's the intuition on matched filtering. All right, there's a cousin of the cross correlation called the autocorrelation. Looks almost the same, except you use just a single time series and let that single time series stand in both slots in this operation. So you are measuring the resemblance of a time series with itself, which seems a little odd to say, but doing it as a function of this time shift. So this has, you learn several interesting things about it. You learn the overall, it's a way of measuring the overall amplitude of this time series. Also, the time scale over which that time series changes, and it's a way of spotting whether there are time scales on which the features in that time series repeat. So this turns out, even though at first glance it sounds a little crazy, why would you go to all this trouble, it's incredibly useful. Perhaps the most profound use for it these days is in its role that it plays in defining the object that we stare at all the time, namely the power spectrum. The power spectrum is the Fourier transform of the autocorrelation of a time series. That's its definition. So here you see autocorrelation, and now e to the minus I2 pi ft d tau, and we end up with the power spectrum as the result of this operation. So, intuition. Like the Fourier transform itself, it's a way of understanding the admixture of sinusoids of all frequencies that make up the time series x of t. But unlike the Fourier transform of the time series directly, it has thrown away the phase information. This is now a real function of frequency. It has no statement about the phase of any particular oscillation. Now, why would you throw away information like that? Why do it? That's a rhetorical question to which I will supply an answer if no one wants to volunteer. The reason is there are situations, and random time series are the prime example, when, this is fun. Can you all still hear me? Yes, there's a signal to noise problem. Okay. If you already have a matched filter for my lecture, I could be quiet and we could play the matched filter. Thank you all. Okay, that's a lot better. All right. So, when you've got a random time series, why should it be picking out a particular phase, a sine versus a cosine of some frequency? There's no information there if it really is random. So it's just too much baggage to carry around the real and the imaginary parts, or the sine and the cosine part of a time series. You'd go crazy looking at both. You should combine them if your purpose is to characterize a random time series. Okay. Now, in a few slides, I will have something else to say about the relationship between power spectra and Fourier spectra. But let me first point out that the classic definition of the power spectrum involves both signs of F, positive and negative frequencies. For historical reasons, but I was brought up in this culture, I know of no experimenter who is interested in looking at the negative frequency scale, and therefore we've invented an object that my favorite notation for is lowercase x squared of F, that is twice the power spectrum at high frequencies, at positive frequencies, and 0 otherwise. And so from now on, we will be looking at so-called single-sided power spectrum. Now, I will let you in on a secret. Nobody ever calculates a power spectrum by carrying out this operation, at least no one that I know. Because there is this very expensive time domain operation involved, the autocorrelation function. And we have wonderful algorithms based most famously the fast Fourier transform that let us do frequency domain operations very efficiently, but time domain ones not. So, yeah.
Should we worry too much that it's minus infinite times or plus infinite times?
Hopefully not. Okay. Well, by the time you're actually done applying this stuff, we will have made a lot of approximations. For example, I'm writing this as if we're doing continuous mathematics, but we do discrete mathematics, okay, sample data. So when you need to understand this, I think I will show you, well, I'll already be showing you one situation where you acknowledge that you're doing a finite amount of time and then talking about limits. You learn how to normalize things so that the particular choice of time duration for your data doesn't really matter. Now, it's important in all of this that if we're using something like the power spectrum, we're either assuming that we're talking about something that's truly stationary, or we want to divide it up into finite amounts of time, recognize the non-stationarity, and say, okay, this is an approximation to what would have been if I had something that was stationary and looking like this. Okay, now here is the way that everyone calculates the power spectrum these days. Take a section of a time series of duration capital T and make sure that you know how to, and in fact do, calculate the Fourier transform that I said no one cares about for random thing. Calculate it. And then form norm squared, and so in norm squared, throw away the phase information this object, norm squared Fourier transform divided by the duration of the time series that you Fourier transform, has a very particular name that you will hear in this learned discussion and then never hear again. This object is momentarily called the periodogram. But then we invoke a theorem that says that in the limit that t goes to infinity, the expectation value of the periodogram is precisely the power spectrum. So what I'm going to do is say, you know what, I just calculated an approximation to the power spectrum. Now, one thing you should never do is believe the mathematician who proved that theorem in this sense. If you say, oh, you know what, I'd really like to take that t goes to infinity limit. So I'm not going to cut my data up into small chunks. I'm going to take as much data as I have and calculate the periodogram. That's a terrible idea, as it turns out, because there's another theorem that says that the width of the distribution that you get on a set of estimates of the power spectrum is as big as the power spectrum itself. So any individual periodogram is a really crummy estimate of the power spectrum, even though the expectation value of that operation is the power spectrum. So in practical applications, the only sensible thing to do, and it's built into every box that you buy that does this at the push of the button, and every well-constructed piece of code that someone will hand you to do this, is to, in fact, take the amount of data that you've got, chop it up into a number of parts, calculate the periodogram on them, and average them. And if you average 10 or 20 or so, all of a sudden you've got a well-behaved estimate of the power spectrum. But never take your whole data set and just calculate this once. Now, why would you even be tempted to use the whole time series? There's one good reason that you're tempted the first time before you get stuck on this, and that is the longer the time you use, the finer is the frequency resolution of your Fourier transform or then your estimate of the power spectrum. So usually say, well, I want good resolution, so I want to take all the data. But you will pay for it really terribly in the huge amount of noise in that single estimate. So instead, I don't think once I started seeing this problem, never looked at an estimate of the power spectrum by the periodogram method without at least 5 chunks averaged together. And that's sort of just barely the beginning. 10 or more seems to be standard. So a word to the wise. But now, let's, instead of getting lost in the weaknesses of this method, let's see what beautiful thing comes out of knowing that the periodogram is a good way, an average of the periodogram is a good way to estimate the power spectrum. And that is, we already had this intuition for the Fourier transform itself, that it's the mathematical object that says I need this much sine and this much cosine of each frequency to sum up to my original time series. But in this situation where we know we oughtn't to care to keep track of sines versus cosines, throw it out by taking the norm squared. Okay? So just knowing that this is a good, useful way to estimate the power spectrum is a way of reminding yourself that what the power spectrum is it's telling you how much of sinusoids without phase information of each frequency are contained in the original time series. Now, just to make sure that everyone has the intuition right, I want to talk about yet another way that the power spectrum could be measured. And in fact, there was a short period of time before the widespread application of digital computers. So we're probably talking the 1940s into the 1960s or 70s, when if you wanted a power spectrum, you might actually spend a huge amount of money to buy a piece of analog apparatus that was set up this way. A bank of bandpass filters, as many with as narrow a band pass for each one as you could afford. So in this intuition building exercise, I'll talk about a bank of bandpass filters, each with 1 hertz passband width and with their passbands centered on integer frequencies, and take that signal and fan it out to the inputs of all those filters. Let the signal be filtered in parallel by that entire bank of bandpass filters, and then at the output end of each bandpass filter, compute the mean square by averaging that output and putting it through a diode. And then you make a display of the outputs of those filter and averaging operations. And that gives you an analog measurement of the power spectrum in that original signal. And today it's sort of horrifying to think that someone might actually have had to go to all this trouble, but you know, horror at the past means happiness about the present. So now, here's something that is worth remembering. And I didn't have to put this theorem on this slide, but this is when I remembered to tell or remind you all that if you summed up all of those outputs of all of those filters, that is, if you perform an integral of the power spectrum over all frequencies, then what you find is the mean square value of that original time series. And that's a way of reminding yourself, if you didn't already spot it here, that the dimensions of the power spectrum are units of original time series squared. Here you would be tempted to say units of original time series squared seconds, but we always will say units of original time series squared per hertz. And then you integrate over all frequencies and the per hertz goes away, and you've got something with the units of original time series squared, and in fact you get the mean square. Now, for some power spectra, it makes sense to actually imagine doing that operation. For others that are strongly colored, such as, our power spectra like always go crazy at low frequencies, and that's actually a pretty general property of measuring instruments, that at low enough frequencies the noise is really huge. So when you interpret a statement about the integral over all frequencies is the mean square, you should really say the integral over all frequencies that I care about is the mean square of what passes through a filter that includes all the frequencies that I care about. It's almost never a well-defined operation to say what's the mean square value of something imagined over all frequencies. Strong noise at low frequencies is just too generic. Okay, we're almost done with this applied mathematics. But just as experimenters hate two-sided power spectra and insist on inventing this one-sided power spectrum for reasons that I have less understanding of, but I was brought up this way too, so I participate in this cultural trait. It is strongly traditional to plot not the power spectrum itself, but the square root of the power spectrum. Okay? And we call it the amplitude spectral density. And almost always, if you check the units on the left-hand side, on the left-hand axis, you will see that you're looking at something that looks like a noise power spectrum, but instead of units of meters squared per hertz, it will say meters per root hertz. Did we see that? Oh my goodness. Yep. meters per root hertz. What's the advantage? Well, the numbers kind of go with the meters, and so if you were looking at a section of a time series on a scope and you were looking for how much wiggling it was, all right, you wouldn't have to square anything that you read on a scope. That's the advantage. The numbers would be kind of close. They'd be in the same ballpark. What's the disadvantage? What in God's name is a root hertz? What it is a reminder that if you're about to do an integral and want to find out how much noise goes through any finite band of frequencies, the very first thing you'd better do is re-square it back to get the power spectrum, because it's only integrals over true power spectra for which the integral operation makes sense, for which the units even make sense. So even though I'm making fun of my colleagues and saying we have limited minds, we remember this and we know we switch back when we have to do any mathematics, but it's a tradition, and so live with our tradition, because we're the ones who are going to be producing the plots in the papers that you read. Yes? 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 Uh-huh. I don't think so. And the reason is, I mean, look, before I say, no, that's a terrible idea, let me say thank you very much for reminding me to point out something really important, that since we're talking about integrals, your eyeball integral of something that's on a logarithmic scale is going to be nutty anyway. So on the way to thinking I really am interested in the integral, really you ought to switch out of logarithmic axes, period, on both axes, in fact. The frequency scale, because, yeah, I mean, you want to know that there's a lot more hertz near 1,000 hertz than there are near 100 hertz. But equally well on the y-axis, because we love logarithmic plots because they compress huge dynamic ranges into something that you can read, okay? So I would never give up my logarithmic scales. However, if what I'm about to do is do an integral, I will guess wrong unless I'm looking at a linear scale. So you're absolutely right. Now, why is there no shortcut for doing what we just described? It's because with a random process, each frequency is a statistically independent thing, and the only operation that makes sense to combine all those different frequency bins in a band is to add them in quadrature. That is, to add their squares, and then if you want a number with meters and not meters squared, take the square root at the end. So I don't know a way around that because it's really built into the properties of noise. It's representing that. But yeah, thank you so much for stating that, and let me just mention, prompted by your question, you know, a hard-won rule. If you're trying to figure out what frequencies are really ruining me, or what frequencies are going to have the best SNR for something else, don't try to guess by taking a quick glance at one of these graphs with logarithmic axes. You'll almost always guess wrong. And I've seen it happen over and over. So in the control room at our various observatories, I think we're actually handicapped by people not remembering to switch back to linear scale before they take a vote on which noise term to work on this week. Okay. But there it is. Having said that, let me defend logarithms anyway, okay? We are talking about things with huge ranges of values. And if I thought, for either this reason or some other reason of purism, that I was only going to show you linear scales, you wouldn't be able to see most of what I wanted to show you. First of all. Second of all, and we'll see some of this more tomorrow than today, log-log scales are a wonderful thing for spotting power laws. Okay? And the fact that there's a power law, in fact, 1 power of frequency, that's really important. And the fact that we're not seeing this slope or that slope or that slope is also really important. So there's 2 fabulously good reasons for plotting things on log-log scales. But even so, if you ever need to think about integrals, switch to, suck it up, lose the dynamic range benefit, lose the recognizing power law benefit, and plot a linear scale. Okay. Amplitude, spectral density. Now.
Maybe before you go on,
Yes.
the trap I've fallen into is sometimes I say, oh, it's x of f, it's got the same limits as x of t.
Nope. Yep, it does not. One is meters per root hertz, and the other is meters. And the twain shan't meet unless you go back into power spectrum world and do whatever is the appropriate integral over whatever frequency band is important. In a moment, I'll do an example of how you switch between RMS. In fact, let's just do it. There's yet one more statement. We already did this kind of in that graph showing matched filtering. Sometimes you just want a number, a single scalar says the noise is this big. If that's what you're aching for is usually the square root of the mean square of the wiggles that you see on a graph. So if you need one number, usually it's the root mean square, because root mean square of a time series has the same units as the time series. And it was actually important at various times to be able to say, okay, GW 150914, it had a peak amplitude of 10 to the minus 21, and okay, the size of the wiggles that we were seeing it over was about this, 10 to the minus 22. So within about a factor of 2 that I can't do better than that by just staring at a graph, all right, we were seeing it with an SNR of around 10. So just saying the size of the wiggles is about 10 to the minus 22 is a good way, a useful way of characterizing the noise in a rough and ready scalar way. However, let me warn you, right? When you've seen these graphs that we show all the time that I showed on Tuesday of the signal that you could see in the noise, I may have remembered to say, but I probably didn't because we usually didn't, that the output time series that we present as the result of our measurement had to have been filtered by someone who had some sense. Otherwise, you wouldn't have seen that signal, because the data as recorded contained, for good reasons, much lower frequencies than we care about in this case, in particular much lower frequencies than frequencies at which the signal to noise ratio was good. So just pulling a chart out of the computer and putting it up, you would not have seen the signal. Filtering always happens. If you're not filtering things, you're not using your mind when you're looking at data. So this HRMS, as I'm about to make explicit, is an RMS calculated over some appropriately chosen frequency band. Let me make that more explicit here. So when I say that, okay, for the detection of a particular signal, GW 150914 is my favorite, but for whatever, when I say, oh yeah, we were competing with noise with a RMS of 10 to the minus 22, first of all, I was saying that, okay, that's the scatter in individual strain measurements that I might put as points on a time series to show the public. And okay, perhaps, I don't know if this was the exact choice made in those graphs, but Okay, maybe sampled every 10 milliseconds. That had a value of 10 to the minus 22. What does that say about the underlying power spectrum or amplitude spectral density of, of the noise that allowed that to be the RMS? It said, what I'm really saying is that the integral over an appropriately chosen band of the single-sided power spectrum of H integrated over, and I'm going to say, all right, we were looking mainly at 100 hertz. 10 milliseconds duration translates into 1 over 10 milliseconds width in hertz. So 1 over 100th of a second is 100 hertz. So the integral from my favorite frequency, 100 hertz, minus half of 100 hertz or plus half of 100 hertz means the integral from 50 hertz to 150 hertz of the power spectrum is this RMS squared, because this operation gives me a mean squared. So a statement like this turns into a statement that the amplitude spectral density was 10 to the minus 23 per root hertz. Let's make sure we can do this. This is 10 to the minus 23 squared. It's 10 to the minus 46, constant over 100 hertz. So it becomes 10 to the minus 46 times 100, or 10 to the minus 44. Take the square root to get back into amplitude spectral density land, and we're talking about 10 to the minus 23 per root hertz. All right, so this is the operation that you need to do either explicitly or you get used to it and don't think about it, to go back and forth between RMS measures, which just tell you the width of wiggles that you see on a noisy time series, width of wiggles that you see on a noisy time series, and what the underlying noise power spectrum or amplitude spectral density was.
Trying to get used to this notation. So that h of s squared is the h of s, which is twice the double-sided.
Yes.
And not the h of f Fourier transform of h of t.
Yeah. Yeah. Okay. I think these slides have a consistent notation, but they're going really quickly, so thank you for asking that clarified thing. So yeah, this is the single-sided power spectrum integrated here, and that means if this were the case that the RMS was 10 to the minus 22, we were dealing with 10 to the minus 23 per root hertz in the vicinity of 100 hertz. Okay. Yes. Yeah. Because I was imagining that I wanted to find a signal of about 100 hertz frequency with optimal SNR, so I wanted to average over a half cycle or something, so I may be off by a factor of 2, and what I said was like the optimal sample frequency, but it's something like this. If you want to see the best contrast, you want to be sampling at just fine enough to see the finest features, but no finer, because you'll blur out the signal in the noise if you sample too finely. All right, I think I just have one more statement of how we translate things. Remember that although we should always be thinking about noise in units of strain, because gravity waves come to us with amplitudes measured in strain, as I will especially make clear tomorrow, most of the sources of noise that compete with a gravitational wave's detection come from motions of mirrors. And as a result, often, not always, but often, and you saw it in this case here, the graph that I pulled to illustrate such graphs to you all, even though we're making a strain measurement at the end of the day, the noise has been presented not as strain units, but as equivalent displacement units of the mirror such that it would mimic the strain, such a strain. Now, to convert from displacement units to strain units, we need to divide those meters by the number of meters in the length of an arm. But if we're trying to be clever and say, well, you know what, most of those noise displacements on my mirrors are incoherent, I'd better add them up for each ones. Let me let you take on faith, in case you haven't already heard this, that each arm has two important mirrors, not just the ones I've been drawing up to now. So I've got four things that wiggle by about the same amount. I'm adding them in quadrature, adding their squares. That would mean 4 times the original square, or in the amplitude world, that's a factor of 2 and not 4. So if I know my actual displacement amplitude spectral density, the equivalent strain spectral density is 2 over L times that. Or if I have a strain amplitude spectral density multiplied by L over 2 to get the equivalent displacement spectral density. So it's saying the same thing. H of f near 100 hertz is 10 to the minus 23 per root hertz, to say I need an interferometer with displacement noise at 100 hertz of 2 times 10 to the minus 20. Did I do that right? Pardon? How did I do that? Did I only do that? Oh, I may have forgotten the actual length of LIGO arms. So let's see. 10 to the minus 23, 4 times. Shall we check work? Let's check work. E to the minus 23 times 4 e to the 3 equals, divide 2. Did I do it right? Yeah, okay. I've made worse mistakes, but okay, I got it right. So it's supposed to be L, the length. How far you ride your bicycle down the end. All right, so what we want to be seeing is, was our noise in the vicinity of 2 10 to the minus 20 meters per root hertz? And all right, maybe it's 3. Okay, been a lot of rough numbers, but yeah, I'm talking about the measurement that we made. All right, I'm about to leave all this mathematical technique behind and talk more about physics. But does anyone have any more questions about these various operations or how to interpret them? If not, I will go on. Okay.
Wait, there's a nomenclature here. That's called the sensitivity curve. There's other names that apply, whether it's the dimensionless strain or whatever.
No one is consistent with these names. Most people I know just call it the noise curve. Okay? It's the noise curve, and they don't care if it's h of f or x of, if it's h units or x units or whatever. You're supposed to be able to switch back and forth. Okay, so we're finally going to apply this to a case where we're talking about real noise from physics that we can understand. So recall that an interferometer is a arm length difference to brightness transducer, and so we've changed the problem by putting the gravity wave through an interferometer from a problem that was originally, let's measure a strain, into a problem of how much light is coming out of the output port of the interferometer from moment to moment. And therefore, if we're lucky, we can be in a situation where either the most important or one of the most important noise sources that comes into the interferometer is how precisely can we measure the brightness of that light, and then convert from the transduction coefficient in that to how learning how small a strain can we find. So you've seen this graph before, something about the steepness of this conversion from an arm length difference or a travel time difference, or as I plotted it here, a phase difference into power. So the question is, since we are, wherever we operate here, using a sudden, a time-dependent change in the power to be a measure of either just the noise or what we hope is to see that signal superposed in there. The question is, how precisely can we measure where we are on this vertical axis? And this tells us how to translate into the horizontal axis. So before I evaluate shot noise, I want to point out an essential feature of designing any interferometer for this purpose, that we would be nuts not to make the signal as big as we could before we ask those two beams to interfere and determine a particular amount of light. And the way to do that is to make the arm as long as possible up until the point where you get no more benefit from making the arm longer. And that length, that is the farthest you need to go before you're not getting any more benefit, is to make the arm about the length so that light spends about a half of the gravitational wave period traveling in the arm. Clearly, if I put it in for a whole period of oscillation, the light is picking up more and more phase as it goes for a while, but then it's losing it because the arm is shrinking again. So, was something which is 3 or 4 kilometers long the right choice for the signals we're looking for? No, it was the right choice for what we could build with our budget and our technology or whatever, but there's only a round-trip travel time of 27 microseconds out and back in 4 kilometers. We really want something like something about a factor of 100 longer storage time in our arms. So, for purposes of making a signal look big against the shot noise, what we ought to do, given that we could only afford 4 kilometer arms, is to come up with a way of bouncing the light back and forth in the arm about 100 times. Yes? Mm-hmm.
You can modify the sensitivity of the interferometer live to have better sensitivity.
So to track where the signal is going to be.
Is this being done in this way, like modifying the effective length of the arms?
The short answer is no, not this exact way, but it's a cousin of that I'll gladly discuss over dinner, but it's a trick. It's about 2 tricks downstream from this. This is not something you could modify on the fly, but you're right that people have suggested it. It could be a good idea, but you would do it someplace else. So let's just talk about a fixed modification of our optics from down and back, the way I've been drawing it up to now, to down and back, down and back, down and back 100 times. We actually learned this from the advanced Michelson interferometer. I showed you this picture before. This was not the first Michelson interferometer that A.A. Michelson ever built. There's a paper by Michelson alone, without the name Morley, from 1881, I believe, where he says, you know what, I'm doing this fabulous thing. I'm going to measure the ether drift. I'm going to see the velocity of the Earth through the ether. And I built this interferometer, but when I was done, it didn't have enough sensitivity to see the Earth's velocity. And the problem with the original Michelson interferometer was he just had the way we sketch a Michelson interferometer. Light hits the beam splitter, goes down, hits a mirror, comes back, and we're done. And that just wasn't good enough sensitivity for him. So what Michelson did is he hired an assistant, Morley. And he said, you know what, I want you to improve initial Michelson. and make advanced Michelson with multiple round trips in the arms. And so the famous paper that we all read, here's where the light comes in, here's the beam splitter, boom, 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 boom. And the other path, the light that goes through, 1 round trip, 2 round trips, 3 round trips, 4 round trips before. Oh, no, you know what? It's 8 because it retraces its steps. So I wrote the wrong number on the slide. 8 round trips, the light finally comes back to the beam splitter and observed by eye through this telescope here. Okay? So, adding beam folding as a way of boosting and making a second generation interferometer that works better goes back to the original history of interferometers. Now, notice how Michelson did it. Here in this plan diagram, or here in this perspective diagram, here are those same mirror mounts I called y'all's attention to yesterday. This was a lot of work. It meant buying a bunch of mirrors, machining a bunch of mounts, and aligning all those mirrors separately one at a time. This idea, precisely the freely suspended version of this, has been entertained seriously in our field, but I will tell you about some other ideas that were maybe entertained by more people for longer, one of which is more or less universally adopted. Here is an early idea called the Harriet delay line, and this is a paper, I got this out of a paper by Donald Harriet from the 1960s. He drew it for something with an aspect ratio that doesn't look very much like 3 or 4 kilometers in between meters about this big, but it shows the basic idea. You have a mirror that is near the beam splitter, and the light enters through a hole in it, and then follows doesn't look like it, but a deterministic path, threading its way between these two mirrors, and finally exits through that hole at some angle to the original input, and then that's what goes toward the beam splitter along with something from the Y arm as well. Ray Weiss at MIT loved this, so I spent several years believing this was the way to go, but he was wrong and I was wrong. A much cleverer way, one that has been more or less universally adopted in interferometers, is to replace the large mirrors with beam spots side by side on that pattern with much smaller mirrors that form, and I'll say a polysyllabic name, resonant Fabry-Perot cavities. And the idea is I can take a mirror, and instead of sending the light through a substantial size hole in a substantial size mirror, I can have a mirror near the beam splitter that is somewhat transmitting. And there's an art to choosing how far away from perfectly reflecting you want. Can't be perfectly reflecting, but it can't be too transmitting either. It doesn't work. So an artfully chosen amount of light transmitted through that first mirror, a very high reflector at the other end of the arm, 3 or 4 kilometers away, aimed to reflect things right back to that original mirror, and then there is some interference magic that I will sketch for you. And interference does the trapping as long as you properly set the distance between the mirrors. And here is some mathematics that I do not want to go through. I put it there for completeness to show you what it might look like. And when these slides are posted, you all can check this work for yourself. But here is a sketch of the input mirror with non-zero transmissivity, the output mirror, which the algebra is allowing for some transmission, but we usually try to make that very, very small. And the idea to understand how this might work is to say, all right, here's the electric field of the input beam. A little bit is going to be promptly reflected, but most is going to go through. Some will be, and that light will be reflected here and come back here. And if I want to see what comes back towards the beam splitter, if I want to build up a calculation of what's called the reflected light, I want to superpose the electric field that's instantaneously reflected from the electric field in the light that goes all the way down and back and is transmitted once. Some of it leaks out, but most is reflected, so most of the light goes and does a second round trip. A little bit leaks out, sum that up. Most of the light is still reflected, comes back, and so we've got a power series. And here is, without any art to it, just term by term, the total reflected light going back towards the beam splitter is the promptly reflected light, the light that passed through the input mirror twice and was reflected once from the far mirror, and then the light that did the same thing a second time, a third time, and so on. And the total field comes from summing up that power series, and the sum has a not very hard to interpret form, but note in particular that it's got a denominator where there's a 1 minus something where those two factors that are both close to 1. So if you adjust the separation of the two mirrors properly, and properly means some integer number of half wavelengths, then you get the kind of constructive interference that gives you a strong beam coming out, because you've also trapped the beam. And if you had little dust motes, God forbid, floating in the cavity, you would see bright light inside. Or if you let a little light leak out the transmitting mirror, you see that you've built up inside, also by the same resonance denominator, a huge amount of power. Now, I consider it somewhat miraculous that whether light is trapped between two mirrors or not is something where you can change the answer between yes and no just by moving one of the mirrors by a small fraction of a micron. But it is true. And not only is it true in the sense that the power builds up, but it's also true that if you have the mirrors at that proper separation, it's called on resonance, for at least very small departures to the left or the right from the perfect position, the phase on the light that's going back towards the beam splitter, the phase that we're calling the reflected light, is a very steep function of separation between the mirrors of cavity length, just as if you had, instead of doing this interference magic, done 100, say, discrete round trips. It's in every way is like the light actually being inside there. And you can wreck it by moving the mirror just a small fraction of the half wavelength away. You're no longer in resonance, and you're out in these parts of the curve where not only is there not a steep dependence of phase on position, but it's even got the wrong sign. I mean, it's horrible. Why in the world would you do this? It's a really twitchy, really tricky thing to build and to make work. However, the advantage of being able to build a working interferometer out of mirrors that are only this big, with masses measured in tens of kilograms, versus needing what it would have taken for the Harriet delay line solution, mirrors like a good astronomical telescope mirror size and expense and mass, is a tremendous advantage. There are some other technical advantages as well. We could go on and on about why it was crazy to think a Harriet delay line was a good idea when this was on offer, but that's the main advantage. The disadvantage is that the interferometer doesn't even come close to working unless all of the mirrors are in almost precisely the right spot. So there's a tremendous bootstrapping problem. So I've installed all the parts. Well, it may take weeks for you to turn it on. To find the procedure, we've now gotten smart, okay? It wouldn't take weeks today. Before the end of our time together, I think on Monday I plan to show you a picture of the celebration in the LIGO-Hanford control room when the first lock of LIGO-Hanford was achieved, when it first was demonstrated to the team sitting there tearing their hair out that yes, they could get all the mirrors in the right places so that the light did what it was supposed to do. Okay? But the benefit is you get everything that a delay line or the original Michelson-Morley solution of multiple mirrors would give with hardware that is just much more compact and therefore affordable.
And is
Yes.
the number of passes then related to how my leaky mirror is?
Yes, you adjust the number of passes by the transmissivity of the input mirror. Okay. Now, you can wreck it by too much loss, but let's assume we got lossless mirrors. The transmissivity of the input mirror is what determines it. Yes. Yes. Okay. As opposed to.
Well, as in when the gravitational wave comes through, it's not.
Okay. All right.
When you showed us that the crests say always stick by in that
Yeah.
equation,
Okay.
always sticking by the mirrors even.
All right. I'm unprepared for the question because the scales of things are so different. This needs to be within a few 10 to the minus 13 or maybe a few 10 to the minus 14 meters versus 10 to the minus 18 meters. So I don't need to think about relativity when I find the resonance. Okay. Would that we had that problem and that then I was prepared to give you a sharper answer. But we don't. Okay, so now we're ready to think about shot noise for real. So I'm going back to, and I'm going to not make the same mistake I made yesterday and quote the H sensitivity of Michelson's interferometer. I'm going to say if I could only tell the difference between constructive and destructive interference, and that set my cavity length measurement that I could make, so of order a half or in the round trip case a quarter of a wavelength. Wavelengths are about a micrometer, 4 kilometer arms, 100 passes. That would mean that I could tell the difference between whether a wave with an amplitude 10 to the minus 12 was present or not. But we want 10 to the minus 22. And therefore that says rather than measuring light is on versus light is off, I want to make a measurement, oh, light has changed by a part in 10 to the 10 of fully on. That's what I need to do if my interferometer with all this great technology, 4 kilometer arms, 100 round trip passes, I still need to make light brightness measurements with the precision of a part in 10 to the 10. Is it possible? Yes. Just barely, but it is possible. In the situation that has been achieved numerous times, numerous places, and that LIGO and Virgo now achieve routinely, at least at high frequencies, we can be in a situation where the most important noise is the granularity of light. The fact that light is made out of photons and that I necessarily will have Poisson fluctuations in the arrival rate of a beam of light at my photodetector. As a hand up. Yes. Yes. Yeah. Yeah. Yes. I don't think it's a problem. Here's how I think of it. The beam that I'm thinking of is the light that makes it to the photodetector, which is the superposition of the two so-called reflected beams from the two arms. Now, have I sat and photon by photon thought of the way to do my optics? I will admit I do classical optics until the last step, but that seems to work. So the question is, what is it that governs the final noise? And you can think of it as just the noise in the beam that you've tracked classically all the way through. I don't think I have to think about it photon by photon through the interferometer. I will maybe lose some sleep over that tonight and see if I can give you a sharper answer, but I I don't think one needs to do that. So, if we want to make a part in 10 to the 10 measurement, if we're fortunate enough to have no noise bigger, and we've proven by example that there are situations where there's no noise bigger than the fluctuations in arrival of light that has the level of Poisson fluctuations, then to have our Poisson fluctuations be a part in 10 to the 10, we need 10 to the 20 photons per measurement interval, because square root of 10 to the 20 is 10 to the 10. Here is a way of turning a certain number of photons per time into power in watts. This corresponds to something measured in kilowatts. Now, this is a lot of photons. That's a lot of light power. We actually achieved more or less this sensitivity with about 20 watts of laser power and a trick I'm about to describe. But let me show you that, in fact, this blue curve is hitting that level, that target that we were expecting, 10 to the minus 23 per root hertz, around 100 hertz. And the fact that the measured curve is on top of the blue curve there is an indication that the careful calculation of the strength of shot noise fully explained the light in those frequencies from 100 hertz on up. Now, let me remind you of the original model that was not going to be adequate, then adding these Fabry-Perot cavities, which for the parameters that we have chosen have this roughly optimum number of about 100 round trips, specifying the transmissivity of those mirrors. But now let me say a bit about power recycling. It's something that the first time you hear it, you say, are you nuts? Can that possibly be right? But it's a great trick. So, what I'm about to tell you is that if you want more light to go into the interferometer, you want to put a mirror blocking the path between the laser and the interferometer. Does that make sense? Let me convince you that it does. All right, I'll say it with this diagram. This is not a perfectly reflecting mirror. This is a mirror with artfully chosen transmissivity. I need to hunt and find the right place. Most places are not good, but every half wavelength, there is a magic place where I've created a resonant Fabry-Perot cavity with this as the input mirror, and all of these other optics thought of as a highly reflecting end mirror. And when I take that mirror with the artfully chosen transmissivity and put it in precisely the right place, I can have 50 times more light power moving to the right of that mirror than I have coming into the back side of it. And it works. It's great, okay? Because, all right, at any given time in history, I can maybe buy a 2-watt laser, or now I can buy a 20-watt laser relatively easily. But I can't buy a 1,000-watt laser so easily. But with this extra mirror and all of the finesse and controls and whatever that go into making it work, it's as if I bought a kilowatt laser. It's too good a trick not to use. Now, just as a warning that you didn't learn everything you need to know here in today's lectures, here is an actual, although simplified still, optical diagram of advanced LIGO, but we can read it. There's the beam splitter, there's the laser, ETM for n-test mass, ETM for n-test mass, very highly reflecting. Here are the input mirrors labeled as ITMs. All right, compensation plates are of some technical interest. Here is the power recycling mirror. We bounce it off of these things. Notice the beam getting wider. That's because we need beams of a certain diameter to be the minimum diffraction beams in the long arms. That's not the way you want to build your laser, so this is a telescope that blows up the beams. What else do I want to show you? The other thing that I want to call your attention to without being able to do justice is that there's actually another mirror blocking the light getting out of the interferometer and falling on the photodiode. That's a so-called signal recycling mirror, and that's there, and it only does its job if you find precisely the right spot to create yet another resonance on the light carrying the signal towards the photodetector. And there's a variety of different styles of resonance that do different functions. It's part of the reason I don't want to explain it, but I do want to point out that not only do we block the light from getting into the interferometer, we block the light from getting out, but with good reasons in both cases. There's other things that filter the beam, and one could spend a day going through this and maybe start to scratch the surface, but those are the basic ideas. And when we didn't have at least most of these tricks working, we didn't have enough sensitivity. So in the remaining couple of minutes, I just want to tip my hat a bit to the evil twin of good shot noise, and that is radiation pressure noise. And I won't get very far in it today, but I do want to point out that we do believe in quantum mechanics. We do believe we're trying to make a pretty darn fine position measurement, at least a differential position measurement, from a set of a couple of mirrors. And so one has to ask the question, does quantum mechanics itself say that that there's a limit to the precision with which you can measure the separations between those mirrors? Because if that limit exists, and if it's too big, then we have to go home. Okay? So here is a sketch of kind of the classic thought experiment in quantum mechanics that says for optical measurements of position, there is a quantum limit. So this is the so-called Heisenberg microscope. But when I read the papers, the original papers, I realized it was Bohr, who was the only one who understood it at the time. So we should call it the Bohr microscope, but whatever. They both get plenty of credit. So here's the idea. You've got a source of light, and you're trying to determine the position of an atom, maybe it is an atom, by having some of that light reflected by the atom, and then you see that it's been reflected because you pick up the light by viewing it through a microscope. And it sounds pretty good, but Bohr was able to show that just from thinking about photons traveling through optics, that you could see that there was an unavoidable combination of unavoidable minimum product of position uncertainty and momentum uncertainty of the object whose position you're going to measure. And now that I understood this, I kind of like it, because if you want to get a precise measurement of where that atom was, you want a big objective lens in your microscope, because the limit to the precision is going to be diffraction. Okay. But if you're collecting light over a big objective lens in your microscope, you're collecting light that could have bounced at a variety of angles off of that atom, and therefore the momentum kick that's applied to the atom is uncertain, and it gets more uncertain the more you try to improve your position sensitivity by opening up the objective lens of your microscope. And that's the way you see that in this particular apparatus there is an uncertainty principle where the product of delta x and delta p must be greater than h bar. Now, what is the equivalent of that for an interferometer? We improve our position measurement by having more and more light power, more and more photons. That's great. And as we saw, our precision, delta x, goes down like the square root of m. But those photons are giving momentum kicks to the mirror, radiation pressure. And the strength of that, of the fluctuations in that pressure grows like the number of photons that are hitting the mirrors. So if I thought that I could, without limit, just send more and more light into an interferometer and reach arbitrarily good precision, I would have been fooling myself for a reason very much like the Heisenberg microscope. The, um, the random pushes on the mirror grow as you shrink your position resolution. And if you work out the minimum product, which I'm not going to do today, you will see, in fact, it is another version of quantum mechanics biting you. Too much power can, under some circumstances, be as bad as too little. I'll call your attention to the thing that I'll explain in a little more detail tomorrow. At low frequencies, that's where radiation pressure noise hurts you. And so shot noise is this white thing here. You can ask me over dinner why it's sloping like 1 power frequency and not white all the way there. But this is the 1 over frequency squared characteristic that you expect from the fact that applying kicks to a mass at higher and higher frequencies, inertia resists more and more. I'll explain that more later. But there is the radiation pressure noise for the amount of light power in O1. So you can see that this was not yet a limiting noise term, but we have ambitions to use quite a bit more light power. This will come down, this will come up, and there will be situations where, at least at some frequencies, the radiation pressure noise may be the strongest, at least strongest understood source of noise. So, have more on that tomorrow, but it's time for us to break. So thanks for your attention. Any more questions quickly before we all break? Okay, see you all over at dinner.